what is wave impedance? Wave impedance, you can, any impedance is represented by eta. Eta can be Ex by Hy or minus Ey by Hx. Now we are writing this wave impedance as an example for TEM wave. TEM wave where we had only Ex and Hy. So we are writing this way. Previously we have we have derived the equations, and so from there we are substituting and getting this value. Now what is attenuation? You have already heard many times about what is attenuation. Now we will derive a general relationship for how to find out attenuation of a wave. Now consider the voltage wave and the current wave. As I previously said, any equation can be written as V equal to V naught into e power minus gamma bar z. I also said gamma bar can be written as alpha plus j beta. The same I am substituting it here, that is V is equal to V naught into e power minus alpha z plus minus j beta, that is V naught into e power minus alpha z into e power minus j beta z. That is the same equation here. This is a relation for voltage, and we can get a similar relation for current. So now we can write, the power can be written as half real part of voltage multiplication of voltage and conjugate part of current. This is the relation that we write usually for power. Power is, pointing vector is E cross H. Now this is half into real part of this 1 and 2 can be substituted here. Half real part of V naught I naught star into, because beta is 0 here, we are not propagating. So V naught e power minus alpha z into I naught e power minus alpha z. So V naught I naught e power minus 2 alpha z. You are just adding these both terms. So now here you can derivate this equation, that is say equation 3. What do you get? You derive it with respect to z, propagation direction, that is dou WAV by dou z is minus 2 alpha. We get some term and it can be replaced by WAV. So you get this minus sign this side and you get this equation. Now we have this equation 4. Say it is equation 4, and now from here you can write this alpha is minus, alpha can be written as half of power lost per unit length by power transmitted, because you say WAV is your power transmitted, then power lost per unit length is this term. So you get a general expression for attenuation of any wave. From this you can take the case of TE or TM or TEM. You can derive the alpha for that particular mode, which I will be explaining later. Now we have completed the topic of attenuation and wave impedance. Now you come for the topic of velocity of propagation. It is generally said to be the physical interpretation of the velocities. The velocities are generally, we have two kinds of velocities, phase velocity and group velocity. We already know what they are. V is the velocity, free space velocity, that is it is c, 3 into 10 power 8. Now in general cases our phase velocity will always be greater than free space velocity and group velocity will always be less than our free space velocity. Now now except for the TEM wave, the velocity with which an electromagnetic wave propagates, that is in an air dielectric between a pair of parallel planes, is always greater than c. That c is free space velocity of electromagnetic waves. So, and one more important concept is, in either rectangular waveguide or cylindrical waveguide, a TEM wave cannot exist. This is an important point which we have to remember, because in the further lectures, when we are deriving the field equations of rectangular and cylindrical waves, we are not going to consider TEM wave because it doesn't exist. And now in this particular topic, we are going to find out the relations between the phase velocity and group velocity. Now to derive the relation between both, you consider a wave, water wave, that is approaching a shore, a seashore, at an angle, say theta. This is our direction of wave travel. Now this is our shore. The z-axis represents our shore. Now you can see that the direction of wave travel is making an angle theta with our breaking water, that is shore. And we have also indicated the velocities in the z direction, in the x direction. Now you can find out the relation by estimating the values of lambda bar and lambda. Lambda bar is nothing but it is the distance between the crest, the two crests offshore. This is onshore. That is, you are going into the water and determining. Here you are not going exactly into the water. You know a basic relation, that is velocity is equal to multiplication of the wavelength and the frequency. If you know the frequency and also the lambda, that is which we are going to estimate, you can easily identify what your velocity of propagation will be, and you can estimate phase velocity, group velocity, and the relation between them also. Now let us not go into the water. So the velocity of propagation here will be lambda bar into f. This is the frequency, and I have said that lambda bar is distance between the two crests along the shoreline. Now lambda bar can be written as lambda by cos theta from the figure. Look at the figure. This is lambda and this is lambda bar. You consider, this is also lambda. This is a right angle. So you can write this. You can easily get this relation. Lambda bar is lambda by cos theta. And you know this relation. So you can write V bar is equal to C by cos theta. Now when this theta is very small, that is your direction of propagation is almost parallel to the shore. That is, it is like this almost. That is, theta is very small. So in that cases, your phase velocity, that is your V bar, will almost approach C. But this is not the case when this is almost 90. This can be either case. That is, your direction of propagation of wave can be either almost 0 or almost 90. But when it is almost 90, that is, your theta is very large, your V bar will also be very large than C. Because cos theta, when you vary theta from 0 to 90, as angle increases, your cos theta value will decrease. When your cos theta value is decreasing, something 1 by cos theta value will obviously increase, and so V bar will also increase. So this is what we have seen. Now let us consider this is a parallel plate waveguide where these both are the plates, and this is the direction of propagation. It is starting like this, making an angle theta, and the distance between the plates is considered to be A. Now, so this wave is propagating like this. This is the z direction, that is direction of propagation, as I have been saying previously. Now lambda, this is the equation we have written. Lambda bar is lambda by cos theta, that is cos theta you have to derive and substitute here. So for this boundary condition to satisfy, you know that A should be m lambda by 2. Here lambda is lambda x. So m lambda x by 2 is equal to A. But you also know that lambda x is lambda by sine theta from the figure above. So sine theta is lambda by lambda x. Now this has to be substituted here. Lambda x is 2a by m. So our sine theta will be lambda by 2a by m. So this is m lambda by 2a. Now you have to substitute this cos theta here, but we have sine theta. But we know that cos theta is root over 1 minus sine square theta. So sine theta is here. We are substituting it here. Lambda by 1 minus m lambda by 2a whole square. And the same thing with v bar is equal to c by cos theta. And c by cos theta is again replaced from sine theta. We also know that group velocity can be written like this. Vg is equal to c cos theta. So again cos theta you are replacing c into root over 1 minus m lambda by 2a whole square. And from this equation and this equation you can conclude that v bar into vg is equal to c square. This is the relation that we derived here. V bar is phase velocity, vg is the group velocity, and c is the free space velocity.